Measurement, from Old French, mesurement, is the assignment of numbers to objects or events. It is a cornerstone of most natural sciences, technology, economics, and quantitative research in other social sciences. Any measurement can be judged by the following meta-measurement criteria: values, level of measurement, which includes magnitude, dimensions, units, and uncertainty. They enable comparisons to be done between different measurements and reduce confusion. Even in cases of clear qualitative similarity or difference, increased precision through quantitative measurement is often preferred in order to aid in replication. For example, different colors may be operationalized based either on wavelengths of light, or qualitative, terms such as green and blue, which are often interpreted differently by different people. The science of measurement is called metrology. A typical tape measure with both metric and US units, and 2 US pennies for comparison. 7 External links. Standardization of measurement units. Measurements are most commonly made in the SI system, which contains 7 fundamental units: kilogram, meter, candela, second, ampere, Kelvin, and mole. 6 of these units are artifact-free, defined without reference to a particular physical object which serves as a standard. The definition of one remaining unit, the kilogram, is still embodied in an artifact which rests at the BIPM outside Paris. Eventually, it is hoped that new SI definitions will be uniformly artifact-free. Artifact-free definitions fix measurements at an exact value related to a physical constant or other invariable phenomenon in nature, in contrast to standard artifacts which can be damaged or otherwise change slowly over time. Instead, the measurement unit can only ever change through increased accuracy in determining the value of the constant it is tied to. The 7 base units in the SI system. Arrows point from units to those that depend on them. As the accuracy of the former increase, so will the accuracy of the latter. The first proposal to tie an SI base unit to an experimental standard independent of fiat was by Charles Sanders Peirce, 1839-1914, who proposed to define the meter in terms of the wavelength of a spectral line. This directly influenced the Michelson-Morley experiment. Michelson and Morley cite Peirce and improve on his method. Standards. With the exception of a few seemingly fundamental quantum constants, units of measurement are essentially arbitrary. In other words, people make them up and then agree to use them. Nothing inherent in nature dictates that an inch has to be a certain length, or that a mile is a better measure of distance than a kilometer. Over the course of human history, however, first for convenience and then for necessity, standards of measurement evolved so that communities would have certain common benchmarks. Laws regulating measurement were originally developed to prevent fraud in commerce. Today, units of measurement are generally defined on a scientific basis, overseen by governmental or supragovernmental agencies, and established in international treaties, preeminent of which is the General Conference on Weights and Measures, CGPM, established in 1875 by the Treaty of the Meter, and which oversees the International System of Units, SI, and which has custody of the international prototype kilogram. The meter, for example, was redefined in 1983 by the CGPM as the distance traveled by light in free space in 1,299,792,458 of a second, while in 1960 the international yard was defined by the governments of the United States, United Kingdom, Australia, and South Africa as being exactly 0.9144 meters. In the United States, the National Institute of Standards and Technology, NIST, a division of the United States Department of Commerce, regulates commercial measurements. In the United Kingdom, the role is performed by the National Physical Laboratory, NPL, in Australia, by the Commonwealth Scientific and Industrial Research Organisation, in South Africa, by the Council for Scientific and Industrial Research, and in India the National Physical Laboratory of India. Units and systems. A baby bottle that measures in 3 measurement systems: Imperial, UK, US. Customary, and metric. 4 measuring devices having metric calibrations. Imperial and US customary systems. Imperial and U.S. customary measurement systems. Before SI units were widely adopted around the world, the British systems of English units and later Imperial units were used in Britain, the Commonwealth, and the United States. The system came to be known as U.S. customary units in the United States, and is still in use there and in a few Caribbean countries. These various systems of measurement have at times been called foot-pound-second systems, after the imperial units for length, weight, and time, even though the tons, hundredweights, gallons, and nautical miles, for example, are different for the U.S. units. Many imperial units remain in use in Britain, which has officially switched to the SI system, with a few exceptions such as road signs, which are still in miles. Draft beer and cider must be sold by the imperial pint, and milk in returnable bottles can be sold by the imperial pint. Many people measure their height in feet and inches, and their weight in stone and pounds, to give just a few examples. Imperial units are used in many other places, for example, in many Commonwealth countries that are considered metricated. Land area is measured in acres and floor space in square feet, particularly for commercial transactions, rather than government statistics. Similarly, gasoline is sold by the gallon in many countries that are considered metricated. Metric system. The metric system is a decimal system of measurement based on its units for length, the meter, and for mass, the kilogram. It exists in several variations, with different choices of base units, though these do not affect its day-to-day use. Since the 1960s, the International System of Units, SI, is the internationally recognized metric system. Metric units of mass, length, and electricity are widely used around the world for both everyday and scientific purposes. The metric system features a single base unit for many physical quantities. Other quantities are derived from the standard SI units. Multiples and fractions of the units are expressed as powers of 10 of each unit. Unit conversions are always simple because they are in the ratio of 10, 100, 1000, etc., so that convenient magnitudes for measurements are achieved by simply moving the decimal place. 1.234 meters is 1234 millimeters, or 0.001234 kilometers. The use of fractions, such as 2/5 of a meter, is not prohibited, but uncommon. All lengths and distances, for example, are measured in meters, or thousandths of a meter, millimeters, or thousands of meters, kilometers. There is no profusion of different units with different conversion factors, as in the imperial system, which uses, for example, inches, feet, yards, fathoms, rods. International System of Units. The International System of Units, abbreviated as SI from the French language name Système International Unites, is the modern revision of the metric system. It is the world's most widely used system of units, both in everyday commerce and in science. The SI was developed in 1960 from the meter-kilogram-second (MKS) system rather than the centimeter-gram-second (CGS) system, which, in turn, had many variants. During its development, the SI also introduced several newly named units that were previously not a part of the metric system. The original SI units for the 6 basic physical quantities were: base quantity, base unit symbol, current SI constants, new SI constants, proposed. Time second SI per fine splitting in cesium 133, same as current SI, length meter, m speed of light in vacuum, c same as current SI, mass kilogram, kg mass of international prototype, kilogram, IPK, Planck's constant, h electric current, ampere rate, permeability of free space, permittivity of free space, charge of the electron, E temperature, Kelvin, K triple point of water, absolute zero, Boltzmann's constant. K amount of substance, smol molar mass of carbon, 12 Avogadro constant, and A luminous intensity, candela, CD luminous efficacy of a 540 Thz source, same as current SI. The mole was subsequently added to this list, and the degree Kelvin renamed the Kelvin. There are 2 types of SI units, base units and derived units. Base units are the simple measurements for time, length, mass, temperature, amount of substance, electric current, and light intensity. Derived units are constructed from the base units, for example, the watt, i.e. the unit for power is defined from the base units as M2, kg, S3. Other physical properties may be measured in compound units, such as material density, measured in kg/m3. Converting prefixes. The SHI allows easy multiplication when switching among units having the same base but different prefixes. To convert from meters to centimeters, it is only necessary to multiply the number of meters by 100, since there are 100 centimeters in a meter. Inversely, to switch from centimeters to meters, one multiplies the number of centimeters by 0.01, or divides centimeters by 100. Length. A 2-meter carpenter's ruler. A ruler or rule is a tool used in, for example, geometry, technical drawing, engineering, and carpentry, to measure lengths or distances, or to draw straight lines. Strictly speaking, the ruler is the instrument used to rule straight lines, and the calibrated instrument used for determining length is called a measure. However, common usage calls both instruments rulers, and the special name straightedge is used for an unmarked rule. The use of the word measure, in the sense of a measuring instrument, only survives in the phrase tape measure, an instrument that can be used to measure but cannot be used to draw straight lines. As can be seen in the photographs on this page, a 2-meter carpenter's rule can be folded down to a length of only 20 centimeters to easily fit in a pocket, and a 5-meter long tape measure easily retracts to fit within a small housing. Some special names. We also use some special names for some multiples of some units. 100 kilograms equals 1 quintal, 1000 kilogram equals 1 metric ton. 10 years equals 1 decade, 100 years equals 1 century, 1000 years equals 1 millennium. Building trades. The Australian building trades adopted the metric system in 1966, and the units used for measurement of length are meters, m, and millimeters, mm, centimeters, cm, are avoided, as they cause confusion when reading plans. For example, the length 2.5 meters is usually recorded as 2500 millimeters, or 2.5 m. It would be considered non-standard to record this length as 250 centimeters. Surveyor's trade. American surveyors use a decimal-based system of measurement devised by Edmund Gunter in 1620. The base unit is Gunter's chain of 66 feet, 20 m, which is subdivided into 4 rods, each of 16.5 feet, or 100 links of 0.66 feet. A link is abbreviated LK, and links LKS in old deeds and land surveys done for the government. Time. Time is an abstract measurement we have invented in order to keep track of elemental changes over a non-spatial continuum. It is denoted by numbers and / or named periods such as hours, days, weeks, months, and years. It is an apparently irreversible series of occurrences within this non-spatial continuum. It is also used to denote an interval between two relative points on this continuum. Mass. Mass refers to the intrinsic property of all material objects to resist changes in their momentum. Weight, on the other hand, refers to the downward force produced when a mass is in a gravitational field. In free fall, no net gravitational forces, objects lack weight but retain their mass. The imperial units of mass include the ounce, pound, and ton. The metric units gram and kilogram are units of mass. One device for measuring weight or mass is called a weighing scale, or, often, simply a scale. A spring scale measures force but not mass. A balance compares weight. Both require a gravitational field to operate. Some of the most accurate instruments for measuring weight or mass are based on load cells with a digital readout, but require a gravitational field to function, and would not work in free fall. Economics. The measures used in economics are physical measures, nominal price value measures, and real price measures. These measures differ from one another by the variables they measure, and by the variables excluded from measurements. Difficulties. Since accurate measurement is essential in many fields, and since all measurements are necessarily approximations, a great deal of effort must be taken to make measurements as accurate as possible. For example, consider the problem of measuring the time it takes an object to fall a distance of 1 meter, about 39 n. Using physics, it can be shown that, in the gravitational field of the Earth, it should take any object about 0.45 seconds to fall 1 meter. However, the following are just some of the sources of error that arise. This computation used for the acceleration of gravity 9.8 meters per second squared, 32 feet/s2. But this measurement is not exact, but only precise to 2 significant digits. The Earth's gravitational field varies slightly depending on height above sea level and other factors. The computation of 0.45 seconds involved extracting a square root, a mathematical operation that required rounding off to some number of significant digits, in this case 2 significant digits. So far, we have only considered scientific sources of error. In actual practice, dropping an object from a height of a meter stick and using a stopwatch to time its fall, we have other sources of error. Most common is simple carelessness. Determining the exact time at which the object is released, and the exact time it hits the ground. There is also the problem that the measurement of the height and the measurement of the time both involve some error. Error resistance. Scientific experiments must be carried out with great care to eliminate as much error as possible and to keep error estimates realistic. Definitions and theories. Classical definition. In the classical definition, which is standard throughout the physical sciences, measurement is the determination or estimation of ratios of quantities. Quantity and measurement are mutually defined. Quantitative attributes are those possible to measure, at least in principle. The classical concept of quantity can be traced back to John Wallis and Isaac Newton, and was foreshadowed in Euclid's Elements. Representational theory. In the representational theory, measurement is defined as the correlation of numbers with entities that are not numbers. The most technically elaborate form of representational theory is also known as additive conjoint measurement. In this form of representational theory, numbers are assigned based on correspondences or similarities between the structure of number systems and the structure of qualitative systems. A property is quantitative if such structural similarities can be established. In weaker forms of representational theory, such as that implicit within the work of Stanley Smith-Stevens, numbers need only be assigned according to a rule. The concept of measurement is often misunderstood as merely the assignment of a value, but it is possible to assign a value in a way that is not a measurement in terms of the requirements of additive conjoint measurement. One may assign a value to a person's height, but unless it can be established that there is a correlation between measurements of height and empirical relations, it is not a measurement according to additive conjoint measurement theory. Likewise, computing and assigning arbitrary values, like the book value of an asset in accounting, is not a measurement because it does not satisfy the necessary criteria. Information theory. Information theory recognizes that all data are inexact and statistical in nature. Thus the definition of measurement is a set of observations that reduce uncertainty where the result is expressed as a quantity. This definition is implied in what scientists actually do when they measure something, and report both the mean and statistics of the measurements. In practical terms, one begins with an initial guess as to the value of a quantity, and then, using various methods and instruments, reduces the uncertainty in the value. Note that in this view, unlike the positivist representational theory, all measurements are uncertain, so instead of assigning one value, a range of values is assigned to a measurement. This also implies that there is not a clear or neat distinction between estimation and measurement. Ascertaining the degree measurement error is also a basic facet of metrology, and sources of errors are divided into systematic and non-systematic. Quantum mechanics. In quantum mechanics, a measurement is an action that determines a particular property, position, momentum, energy, etc., of a quantum system. Before measurement is made, a quantum system is simultaneously described by all values in a spectrum or range of possible values, where the probability of measuring each value is determined by the wave function of the system. When a measurement is performed, the wave function of the quantum system collapses to a single, definite value. The unambiguous meaning of the measurement problem is an unresolved fundamental problem in quantum mechanics.